From worldwideweb.++.com/doc/tutorial/. Part 08. A double quote. Learn by listening. Double quote. Exercise. C++ overloads and templates. Overloaded functions. In C++, two different functions can have the same name if their input parameters are different, either because they have a different number of parameters, or because any other parameters are of a different type. We call these double quote, overloaded double quote, functions. For example, consider the following 22-line program, which creates two new functions, both of which are named double quote, operate double quote, colon. Line 01 of 22 / overloading functions. Line 02 of 22, $, include left angle bracket, IOStream right angle bracket. Line 03 of 22, using namespace std, Line 04 of 22. Line 05 of 22, in operate, open parenthesis, int a, int b, close parenthesis. Line 06 of 22, open curly brace. Line 07 of 22, return, open parenthesis, a asterisk, b, close parenthesis, semicolon. Line 08 of 22, close curly brace. Line 09 of 22. Line 10 of 22, double operate, open parenthesis, double A, double B. Line 11 of 22, open curly brace. Line 12 of 22, return, open parenthesis, A/B, close parenthesis, semicolon. Line 13 of 22, close curly brace. Line 14 of 22. Line 15 of 22, int main, open parenthesis, close parenthesis. Line 16 of 22, open curly brace. Line 17 of 22, int x equals 5, y equals 2, semicolon. Line 18 of 22, double n equals 5.0, m equals 2.0, semicolon. Line 19 of 22, cout, double left arrow, operate, open parenthesis, x, y, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 20 of 22, cout, double left arrow, operate, open parenthesis, n, m, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 21 of 22, return 0, semicolon. Line 22 of 22, close curly brace. When that code was executed, as planned, the following output was generated, 10. 2.5. In this example, there are two functions called double quote, operate double quote, but one of them has two parameters of type int, while the other has them of type double. The compiler knows which one to call in each case by examining the types passed as arguments when the function is called. If it is called with two int arguments, it calls to the function that has two int parameters, and if it is called with two doubles, it calls the one with two doubles. In this example, both functions have quite different behaviors, the int version multiplies its arguments, while the double version divides them. This is generally not a good idea. Two functions with the same name are generally expected to have at least a similar behavior, but this example demonstrates that it is entirely possible for them not to. In this bizarre example, two overloaded functions, open parenthesis, that is, two functions with the same name, close parenthesis, have entirely different definitions, semicolon. They are, for all purposes, different functions, that only happen to have the same name. Note that a function cannot be overloaded only by its return type. At least one of its parameters must have a different type. Function templates. Overloaded functions may have the same definition. For example, Consider the following 20-line program, which defines two functions named double quote, sum double quote. One of these operates on integers, while the other operates on double precision floating point numbers. Both functions calculate the sum of the two arguments passed into them, Line 01 of 20 / overloaded functions. Line 02 of 20, $, include left angle bracket, IOStream right angle bracket. Line 03 of 20, using namespace std, semicolon. Line 04 of 20. Line 05 of 20, in sum, open parenthesis, int a, int b, close parenthesis. Line 06 of 20, open curly brace. Line 07 of 20, return a plus b, semicolon. Line 08 of 20, close curly brace. Line 0, 9 of 20. Line 10 of 20, double sum, open parenthesis, double A, double B. Line 11 of 20, open curly brace. Line 12 of 20, return A plus B, semicolon. Line 14 of 20, close curly brace. Line 14 of 20. Line 15 of 20, int main, open parenthesis, close parenthesis. Line 16 of 20, open curly brace. Line 17 of 20, cout, double left arrow, sum, open parenthesis, 10, 20, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 18 of 20, cout, double left arrow, sum, open parenthesis, 1.0, 1.5, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 19 of 20, return 0, semicolon. Line 20 of 20, close curly brace. When that code was executed, as planned, the following output was generated: 30. 2.5. Here, sum is overloaded with two different parameter types, but with the exact same body. Main called sum twice. The first time, integer arguments were passed. The second time, double precision floating point arguments were passed. In both cases, an appropriate version of sum was invoked, and an appropriate total was calculated and returned. Obviously, any function like our sum could be overloaded for a lot of types, and it could make sense for all of them to have the same body, but this would force the programmer to write separate definitions of sum for every type of data that might ever be used with it. To ease the burden on programmers in cases such as this, C++ has the ability to define functions with generic types, known as function templates. Defining a function template follows the same syntax as a regular function, except that it is preceded by the template keyword and a series of template parameters enclosed in angle brackets. Here is the syntax used to precede a function definition to identify it as a template: template left angle bracket, template parameters right angle bracket, function declaration. When using this syntax, the template parameters are a series of keyword and parameter pairs separated by commas. Within a definition that follows this pattern, the programmer can create one or more new words of his own design to represent generic treatment of one or more parameters to be used for the function whose definition immediately follows this template. This is done by invoking either of two keywords, class or type name followed by a new generic identifier of the programmer's choosing. Hereafter, the new generically defined identifier can be used in the function declaration to generically represent any available data type. For example, a generic sum function could be defined, as shown in the following 5-line program segment, in which the programmer chose the new main sum type as a generic identifier to represent any available type of data that might ever be passed in as a parameter. Line 0, 1 of 0, 5 template left angle bracket, type name sum type right angle bracket. Line 0, 2 of 0, 5 sum type sum, open parenthesis, sum type x, sum type y, close parenthesis. Line 0, 3 of 0, 5 open curly brace. Line 0, 4 of 0, 5 return x plus y, semicolon. Line 0, 5 of 0, 5 close curly brace. The basic idea behind this sum template is that the function can accept two arguments of arbitrary type. Those two values will be added to one another and returned, regardless of the type of data received. By using a generic template like this, the programmer is freed from the burden of writing separate, identically named functions for each anticipated type of data. In this example, the programmer used the C++ keyword type name to identify sum type for this purpose, but he could just as well have used the keyword class instead. It makes no difference whether the generic type is specified with keyword class or keyword type name in the template argument list, open parenthesis. They are 100% synonyms in template declarations, close parenthesis. In the code above, declaring sum type open parenthesis, a generic type within the template parameters enclosed in angle brackets, close parenthesis, allows the word sum type to be used anywhere in the function definition, just as any other type, semicolon. It can be used as the type for parameters, comma, as return type, comma, or to declare new variables of this type. In all cases, comma, it represents a generic type of data. The actual data type will be determined when the template is double quote, instantiated double quote. A further definition is in order here, double quote, instantiating double quote. A template is applying a previously defined template to create a function using particular types or values for its template parameters. This is done by simply calling the function template, comma, almost as if it were a regular function, comma, but with one additional detail, colon. In between the familiar function name and parenthesis, a pair of angle brackets must be inserted. Between these new angle brackets, comma, the actual data type or types must be identified. For example, comma, the double quote, some double quote, function template defined above can be called, open parenthesis, or double quote, instantiated double quote, close parenthesis, like this, colon. X equals some left angle bracket, int right angle bracket, open parenthesis, 10, 20, close parenthesis, semicolon. The function double quote, some left angle bracket, int right angle bracket, double quote, is just one of the possible instantiations of the function template named double quote, some double quote. In this case, comma, by using double quote, int double quote, as the template argument, comma, the compiler automatically instantiates a version of some where each occurrence of some type is replaced by int, comma, as if it was defined using these 4 lines, colon. Line 0, 1 of 0 for int some, open parenthesis, int x, comma, int y, close parenthesis. Line 0, 2 of 0 for open curly brace. Line 0, 3 of 0 for return x plus y, semicolon. Line 0, 4 of 0 for close curly brace. For example, comma, consider the following 22 line program, colon. Line 0, 1 of 22 / function template. Line 0, 2 of 22, $, include left angle bracket, iostream right angle bracket. Line 0, 3 of 22, using namespace std, semicolon. Line 0, 4 of 22. Line 0, 5 of 22, template left angle bracket, class T right angle bracket. Line 0, 6 of 22, tsum, open parenthesis, ta, tb. Line 0, 7 of 22, open curly brace. Line 0, 8 of 22, t result, semicolon. Line 0, 9 of 22, result equals a plus b, semicolon. Line 10 of 22, return result, semicolon. Line 11 of 22, close curly brace. Line 12 of 22. Line 13 of 22, int main, open parenthesis, close parenthesis. Line 14 of 22, open curly brace. Line 15 of 22, int I equals 5, j equals 6, k, semicolon. Line 16 of 22, double f equals 2.0, g equals 0.5, h, semicolon. Line 17 of 22, k equals some left angle bracket, int right angle bracket, open parenthesis, I, j, close parenthesis, semicolon. Line 18 of 22, h equals some left angle bracket, double right angle bracket, open parenthesis, f, g, close parenthesis, semicolon. Line 19 of 22, C out, double left arrow, k, double left arrow, single quote, new line, single quote, semicolon. Line 20 of 22, C out, double left arrow, h, double left arrow, single quote, new line, single quote, semicolon. Line 21 of 22, return 0, semicolon. Line 22 of 22, close curly brace. When that code was executed, as planned, the following output was generated, 11. 2.5. In this case, we have used double quote, t double quote, as the generic template parameter name, instead of double quote, some type double quote. It makes no difference, and t is actually a quite common template parameter name for generic types. In the example above, we used the function template double quote, some double quote, twice. The first time with arguments of type int, and the second one with arguments of type double. Accordingly, as we can see from the 2 lines of program output, the compiler has instantiated and then called the appropriate version of the function both times. Note also how t is also used to declare a local variable of that, open parenthesis, generic, close parenthesis, type within some colon. T result, semicolon. Therefore, double quote, result double quote will be a variable of the same type as the parameters a and b, and also the same type as returned by the function. In this specific case, where the generic type t is used as a parameter for some the compiler is even able to deduce the data type automatically without having to explicitly specify it within angle brackets. Therefore, instead of explicitly specifying the template arguments with these two lines line 0, 1 of 0 to k equals some left angle bracket, in right angle bracket, open parenthesis, I, j, close parenthesis, semicolon. Line 0, 2 of 0 to h equals some left angle bracket, double right angle bracket, open parenthesis, f, g, close parenthesis, semicolon. It would be possible instead to simply skip the type information and associated angle brackets. We could just write line 0, 1 of 0 to k equals some, open parenthesis, I, j, close parenthesis, semicolon. Line 0, 2 of 0 to h equals some, open parenthesis, f, g, close parenthesis, semicolon. Naturally, we can only use this shortcut when the type values are unambiguous. If some is called with arguments of different types, the compiler may not be able to deduce the type of t automatically. Templates are a powerful and versatile feature. They can designate multiple template parameters, and, of course, the associated functions can also use any combination of templated, generic parameters and regular non-templated types, exactly as you would expect. For example, consider the following 18-line program, which compares an integer value with a double precision floating point value to see if they both evaluate to the same numeric quantity. In this case, an integer value of 10 is compared with a floating point value of 10.0, and the program evaluates them as equal double quote. The main function of the program relies on a templated function named r underscore equal double quote to evaluate for equality. The template for r underscore equal double quote indicates that two input variables, to be named t double quote and u double quote, each of arbitrary class, are expected, Line 0, 1 of 18 / function templates. Line 0, 2 of 18, $, include left angle bracket, IOStream right angle bracket. Line 0, 3 of 18, using namespace std, semicolon. Line 0, 4 of 18. Line 0, 5 of 18, template left angle bracket, class t, class u right angle bracket. Line 0, 6 of 18, bool r underscore equal, open parenthesis, ta, u me. Line 0, 7 of 18, open curly brace. Line 0, 8 of 18, return, open parenthesis, a equals me, close parenthesis, semicolon. Line 0, 9 of 18, close curly brace. Line 10 of 18. Line 11 of 18, int main, open parenthesis, close parenthesis. Line 12 of 18, open curly brace. Line 13 of 18, if, open parenthesis, r underscore equal, open parenthesis, 10, 10.0, close parenthesis. Line 14 of 18, cout, double left arrow, double quote, x and y are equal, new line, double quote, semicolon. Line 15 of 18, else. Line 16 of 18, cout, double left arrow, double quote, x and y are not equal, new line, double quote, semicolon. Line 17 of 18, return 0, semicolon. Line 18 of 18, close curly brace. When that code was executed, as planned, the following output was generated: x and y are equal. Note that this example uses automatic template parameter deduction in the call to r underscore equal. Specifically, from within our main function, we wrote r underscore equal, open parenthesis, 10, 10.0, close parenthesis. This is equivalent to r underscore equal left angle bracket, int, double right angle bracket, open parenthesis, 10, 10.0, close parenthesis. We were able to avoid writing the details between angle brackets, because, in C++, integer literals with no suffix, open parenthesis, such as 10, close parenthesis, are always of type int, and floating point literals without suffix, open parenthesis, such as 10.0, close parenthesis, are always of type double. Accordingly, there is no ambiguity possible, and thus the template arguments can be omitted in the call. Non-dash type template arguments. The template parameters can not only include generic types introduced by double quote, class double quote, or double quote, type name double quote, comma, but can also include expressions of any pre-defined type colon. For example, comma, consider the following 14-line program, comma, which uses a template to create a new function that multiplies one number of arbitrary type with another number, which is always an integer. Line 0, 1 of 14 / template arguments. Line 0, 2 of 14, pound sign, include left angle bracket, iostream right angle bracket. Line 0, 3 of 14, using namespace std semicolon. Line 0, 4 of 14. Line 0, 5 of 14, template left angle bracket, class t comma, indent right angle bracket. Line 0, 6 of 14, t fixed underscore multiply, open parenthesis, t val, close parenthesis. Line 0, 7 of 14, open curly brace. Line 0, 8 of 14, return val asterisk, end, semicolon. Line 0, 9 of 14, close curly brace. Line 10 of 14. Line 11 of 14, int main, open parenthesis, close parenthesis, open curly brace. Line 12 of 14, std cout, double left arrow, fixed underscore multiply left angle bracket, int comma, to right angle bracket, open parenthesis, 10, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 13 of 14, std cout, double left arrow, fixed underscore multiply left angle bracket, int comma, 3 right angle bracket, open parenthesis, 10, close parenthesis, double left arrow, single quote, new line, single quote, semicolon. Line 14 of 14, close curly brace. When that code was executed, as planned, the following output was generated: 20, 30. The second argument of the fixed underscore multiply function template is of type int comma, named double quote, and double quote. In the template comma, it just looks like a regular function parameter. But there is one major difference: Look carefully at the line that names the function. It looks like this. T fixed underscore multiply, open parenthesis, t val close parenthesis. Note that only one value, named double quote, val double quote, comma, of arbitrary type, is passed into the fixed underscore multiply function. Even though a multiply operation always needs two parameters, comma, and even though the template declares two parameters, comma, the value of template parameters is determined at compile time and cannot rely on any information that is not known when the compiler is invoked. Accordingly, comma, each time the compiler finds a reference to double quote, fixed underscore multiply double quote, comma, it can only generate a different instantiation of the function fixed underscore multiply based on hard-coded constant values like the double quote, to double quote, and the double quote, 3 double quote, found in the to double quote, cout, double quote, source code lines above. Thus the value of those arguments can never be passed during runtime. The two calls to fixed underscore multiply in our double quote, main double quote, function essentially create and call two separate versions of the function: one that always multiplies by 2 comma, and one that always multiplies by 3. For that same reason, comma, the second template argument needs to be a constant expression, open parenthesis. It cannot be passed a variable, close parenthesis.